Acids and bases. In this lesson, we're covering pH, acid properties, HCl, acid precipitation, ocean acidification, base properties, neutralization reactions, cleaning up chemical spills, acid reflux, GERD, and indicators. Acids and bases. Substances are either acidic, basic, or neutral. An acid is a substance that will donate a proton, that's going to be our H plus or our H3O plus, or accept an electron pair in reactions. A base, on the other hand, is a substance that will accept a proton or donate an electron pair in reaction. So they're opposites to each other. A neutral substance is one that doesn't show acid or base properties. pH. We can determine how acidic or basic a substance is based on where it falls on the pH scale. The pH scale is a measure of how acidic a substance is, and it's measured on a scale from 0 to 14, with 7 neutral being things like water and blood, less than 7 being acidic, so that's going to the left, and then anything that's to the right of 7, that's going to be basic, so things like ammonia, other household cleaners, etc. Those are basic substances here. Acids. As I said before, acids release hydrogen / hydronium ions. So hydronium, that's going to be our H3O plus, and hydrogen is our H plus, as it says below, in water. So for example, HCl is going to give us H plus and Cl negative. So since it gives us this H plus ion, that makes it an acid. The pH of acids are less than 7. They're sour tasting, and they're very reactive. So they're explosive and corrosive, and they can be very dangerous. Common examples include things like lemons, limes, HCl, lead acid batteries, wine, etc. Now we're going to take a look at one acid in particular, and that's HCl. So HCl stands for hydrochloric acid, and it's a very important acid that's excreted by the stomach lining and acts to weaken the bonds holding the food together, helping us break it down. It also helps dissolve minerals from various foods, as well as kill bacteria that enter our stomach as we eat the food. So without this acid in our stomach, these little guys here would cause us a lot of trouble. Acids. Acids can also act as preservatives, allowing food to be kept good longer. So if you put an acid into a preservative, that's something that's going to kill the microorganisms, which we just talked about on the previous slide, right? These guys right there. So since we're going to kill those things in and around the food, it's going to allow that food to stay good longer. Another thing acids do is they react very well with metals to produce hydrogen. So the hydrogen gas is highly combustible, as in it will catch fire and explode. So here's an example of it. If you have HCl and you add zinc metal to it, you're going to produce this hydrogen gas, which is highly combustible. Acids. Acids also conduct electricity. So although they are molecular compounds, when placed in water, they collide with the water, breaking the acid into ions. These ions are used to conduct electricity. So HCl is going to be smacked around by all these H2O molecules that they're placed in. And as that happens, it breaks into its ions, H plus and Cl negative. And since the ions have a charge, they conduct electricity. So you'll notice that the chemical formula for acids start with an H and are followed by an AQ. And that's going to always be our clue. So you can see here with our HCl, it starts with an H and it has our AQ in it. So that's going to be our clue that this is an acid. The H itself, the H plus, is responsible for the acid's properties. So examples of this include vinegar, citric acid, lactic acid. Acid precipitation. Fossil fuels are made from dead organisms which have been buried underground for millions of years. This is mainly plants. There are some animal and other organic material included as well, but the big contributor is plants. So when fossil fuels, so when the plants decompose and are crushed under the pressure and the heat over millions and millions of years, they turn into these fossil fuels like coal, oil, and gas, and we burn them to make energy. So during this process, nitrogen and sulfur are released, which combine with oxygen in the air to form nitrogen oxide. So this NOx stands for any kind of NO compound. So it could be NO2, NO3, so that X just stands for that subscript, as well as sulfur dioxide, which is SO2. These then combine with water, so H2O in the atmosphere, to form acids, and that's going to be our nitric acid and also sulfuric acid. These acids then fall to Earth as acid precipitation in the form of rain, sleet, snow, etc. Effective acid precipitation. So as the acid comes down to the ground, it's going to change the pH of the soil and the water that the plants are using to survive. And if those plants are more susceptible to changes in pH, they could die. And typically what you'll see is a given area where there's all kind of a similar tree. And if that similar tree kind is very susceptible to changes in pH, you'll see a whole group of them, like in this picture here, dying off all at once in the same area. It can also cause serious problems in aquatic ecosystems, killing fish, amphibians, and other organisms due to a decrease in pH. Now, this will depend on the organisms itself. Some organisms are better at surviving with a change in pH, while others are less so. So you'll have the species that are less able to adapt die off quicker than the other species, but if the pH changes significantly enough, no species will survive at all. And lastly, it can also destroy stonework. So a lot of the older stoneworks made from things like limestone, which are very susceptible to acid precipitation, when it rains down upon it, it can actually really break them apart. Ocean acidification. So when CO2 dissolves in oceans, it becomes carbonic acid, which decreases ocean pH levels. And this is very common, especially now, because our oceans are giant carbon sinks. So if you think about all the carbon dioxide we're putting into the air, well, not all of it ends up in the air. Some of it falls down to the oceans. And when it does, it gets absorbed by the oceans. And we think, okay, well, that's great. It's a great storage facility for that carbon dioxide. But it's not really the case, because eventually the acidity of the oceans will get to the point where it's going to really affect the ecosystems that are in there. So a couple more stats. So the acidity of the oceans has increased by 26% since 1850. That's pretty significant. And this is approximately 10 times faster than any other time in the last 55 million years. So that is a significant stat. So as a result of this, there will be significant impacts on marine ecosystems. Specifically, a decrease in ocean pH can make it difficult for marine calcifying organisms, such as coral and some plankton, to form shells and skeletons. So if they can make them, often the shells aren't as strong, or perhaps they're not really able to make them as sturdy as they should. So people may not be so concerned about things like coral and plankton, but you got to keep in mind that it's all just a big food web, that if one species is affected, then the next organism that eats it and the one that is eaten by it are also affected. So it can have significant implications up and down the food chain, which will eventually affect things like fisheries, aquaculture, and tourism. Bases. Bases are also called alkaline. They release hydroxide ions in water. So remember, our bases release our H plus and H3O+. Well, bases are going to release OH negative ions. So for instance, NaOH becomes Na plus and OH negative. So a clue to whether or not it's an acid or a base, if it's a base, you're going to see this OH negative as one of our reactants. You can see in the NaOH, we can see the OH right there. Now, some more characteristics. Bases have a pH greater than 7. They taste bitter, and examples include things like drain cleaner, soap, antacids. Bases. Most bases are ionic compounds and therefore dissolve in water into ions. So if you have barium hydroxide, it's going to form Ba2+ and OH negative. Since ions are formed in water, bases will conduct electricity. Bases are also very dangerous. So a lot of people think that acids are the really bad one, the really dangerous thing, but bases can be just as or more dangerous than acids can. Neutralization reactions. When an acid reacts with a base, we get a neutralization reaction. So what is actually happening is that our pH is moving towards 7. So if you have an acid, and let's just say the acid has a pH of 4, if you add a base to it with a pH of 14, then it's going to bring this 4 closer to 7. Now, how close does it get to 7? Well, it depends on how much of this 14 you add. If you add significantly more base with a pH of 14 to the acid with a pH 4, then you might go way past the 7. It might end up closer to 11 or 12. But if you put just the right amount in, you'll end up with a substance that has a pH right at 7. And this is called a neutralization reaction. These reactions are double displacement. So you can see in this example here, we have our HCl plus our NaOH is going to give us this HOH, which is H2O, plus NaCl. And what this is you actually have your base, your acid, your base, and what you get is water and salt. And that's going to be what we form every single time we do a neutralization reaction. We're always going to get this salt and water. A couple more examples here for you. So if you take HCl and add NaOH to it, again, you get water and salt, NaCl. If you take sulfuric acid and you add potassium hydroxide, you again get water and this salt, potassium sulfate. Salts don't just have to be NaCl, and we're going to see on the next slide what a salt is, but it's going to be a product of a neutralization reaction, is going to be our salt. But basically, when we're doing a neutralization reaction, what we are doing is we're taking the H pluses from the acid, we're adding the OH negatives from the base, and we're making water from it. This salt that's also produced is just the byproducts of the other reactants that were involved. So what is salt? Well, salt is a combination of positive and negative ions formed by the reaction of an acid and a base. It's an ionic compound. It can also be rehydrated by adding water to form that acid and base again. So here's a case study. So neutralization, cleaning up a chemical spill. So in 2007, a train containing 150,000 liters of sulfuric acid suddenly derailed and spilled some of its cargo into the nearby river. This resulted in an ecological disaster as dead fish washed up on shore and local residents were warned not to allow their livestock to drink river water. The emergency response crew added calcium oxide, so that's lime, not calcium hydroxide, keep in mind, calcium oxide, and it's a solid, to the river slightly upstream from the spill site in order to neutralize the reaction. So what actually happened? Well, the spill cleanup strategy relied on a two-step neutralization reaction. By adding the calcium oxide, the CaO, we were able to have it react with the water that it was poured into to form our basic CaOH2. That's our base. The calcium hydroxide, that's this guy right there, neutralized the sulfuric acid in the river, producing a harmless solution of water and calcium sulfate. There's our water, and there's our calcium sulfate, our salt. So why don't we just add calcium hydroxide to the water directly? Well, it's a lot safer to carry around this calcium oxide, first of all. It's a lot easier to handle and a lot easier to distribute into the water. So it just makes it an easier process. Application, acid reflux. Now this is something near and dear to my heart. I get acid reflux too much. And so it's something that I'm acutely aware of, as is everyone who does get acid reflux. It's something that comes and goes with age. Generally, as you get older, you get more acid reflux. As you become pregnant, unfortunately, you also develop acid reflux, and it's simply due to the valves inside the stomach that prevent the acid from moving up and down. So let's break it down. So your stomach produces hydrochloric acid with a pH of around 1.5. So it's a very, very strong acid. And we're very lucky that our stomach does this, because without it, we wouldn't be able to break down the food that gets put into our gut. Also, we'd be more susceptible to the bacteria that comes in with the food. But luckily, again, for us, our stomach has a protective lining of mucus, which keeps it safe from the acid, and a one-way valve, which only allows foods and liquids to travel into the stomach. So we're going to have this one-way valve right here. Let's draw it like this. So what this means is that the food can go in, but it can't go out because that valve is closed. And at the beginning, what I said is that we have this protective mucus layer that goes all the way around the stomach, which is, again, very, very good. Otherwise, since this acid is so strong, it would actually eat through the stomach. Now, sometimes people develop things called ulcers, and an ulcer is when you lose a little bit of that mucus. And when you lose a little bit of that mucus, that acid is able to get to the stomach and actually kind of eats away at the stomach. And there's different degrees of ulcers, and they cause significant amounts of pain, and eventually it can be called a bleeding ulcer. A bleeding ulcer is when the acid actually gets into the blood vessels and you start getting some blood into your stomach, which eventually makes it into your stool, and that's very uncomfortable, and that usually requires medical intervention. So continuing on with our acid reflux, it occurs when the acid exits the upper part of your stomach and comes into contact with your esophagus. So as we showed on the previous slide, we have this nice mucus layer all around our stomach, but what we don't have a mucus layer around is the esophagus right here, the bottom part of the esophagus. And that's shown in this diagram right here as well. There's the valve that we were talking about. So when the acid exits the top part of the stomach and splashes into the esophagus, that's when we're going to get that pain, that burning sensation that we often call heartburn. Now, if you have a more exaggerated version of this acid reflux where it happens more often or it's more severe, it also has a name. It's called gastroesophageal reflux disease, or GERD. And it's a chronic, more severe version of acid reflux, like I was just saying. Now, what are the near and long-term consequences of acid reflux? Well, on the near term, it's more of a discomfort issue. It can wake up at night and cause trouble sleeping or eating certain foods. Over a short term, it's not a huge deal, but over a very long term, that acid can actually cause problems with your lower esophagus, and can potentially lead to things like cancer or other problems in your esophagus area. Acid reflux neutralization reaction. So bringing it all together, acid reflux is treated via a neutralization reaction in the esophagus. So we talked about the fact that your stomach produces this HCl, and that's what causes that burning sensation in your esophagus. Now, to counteract that, we take antacid tablets, which are essentially a base that we're going to take. So this acid is splashing up in our stomach, we take in some base, and then we create a neutralization reaction in our esophagus. And that neutralization reaction produces water and this salt. The salt generally just flows back into your stomach, and then you just pass it. Now, the last thing we're going to cover are indicators, and these are just chemicals which change color when they're placed in acidic or basic solutions. They're called indicators because they indicate the pH of the substance. Some are natural, things like red cabbage can be used as a pH indicator, and some are synthetic, like bromothymol. You can also use different kinds of papers as well, which allow us to understand which kind of acidity level we're dealing with. So for instance, in this particular chart, this would be a red cabbage chart. If you have a pH of around 4.5, you'd see this red color, and if your pH was closer to 7.5 or 8, you'd get more of this dark greeny color. So it's a pretty interesting thing to see. And that concludes our lesson on acids and bases.